koutou, hua huhui mai nei, e mihi ana kina mana whenua, ko Troy Coyle no Tamaki Makaurau aho. E mahi anao hei CEO ki hera, no rira ina koutou katoa. Today I'm going to be talking about steel decarbonisation, and we'll start by looking at why steel is considered to be a hard to abate industry, then looking at the global initiatives and the local initiatives to deliver that decarbonisation journey. Steel is the world's largest material industry. It generates a turnover of $1 trillion annually, and it contributes a large component of our national infrastructure, which is driving those steel volume demands and that turnover. Steel is an integral component of our main infrastructure, including our bridges, our road systems, our rail systems, and our building stock, including our homes. And demand for steel is not likely to decline. In fact, it's likely to increase, with the International Energy Agency predicting global demand for steel to increase by more than a third through to 2050. And that demand will be driven primarily from those applications that we just ran through, but also for applications in manufacturing, as well as the global transition to a clean energy economy. And that's because it's also a vital component of the infrastructure required to do that. So it's part of our wind turbines, it's part of our hydro systems through the concrete reinforcing, it's part of our wave and tidal energy systems, our geothermal systems, and even the racking for our solar systems. However, the steel sector is emitting large volumes of CO2. In fact, around 2.6 gigatons of carbon dioxide annually, which is around 7% of the global total from the energy system and more than the emissions from all road freight. So if we are going to limit global warming to that 1.5 target, we have just 30 years to reduce our greenhouse emissions from that 2.6 gigatons to net zero carbon. One of the misconceptions around steelmaking is that the CO2 is being emitted from the burning of coal to provide heat or energy in the processing. That's not true. The reason why steelmaking is considered hard to abate is that the coal is actually required is part of the metallurgical process, basically the chemistry required to create steel. So if we look at that chemical process, we basically take some iron ore, some iron with oxygen attached to it, and we need to remove that oxygen in order to create a more pure version of the iron to then be used in the steelmaking process. And in order to do that, we actually use the coal and the carbon in that coal as a reductant. So it's taking that oxygen away and creating CO2. So the carbon from the coal is actually part of that chemical equation to create steel. And that's why steelmaking is considered a hard to abate industry. If we look at that steelmaking process in more detail, there are two primary processes used globally, and steel mills globally will be using one or the other or a combination of these processes generally. So the first process is the least intensive process, which is basically taking steel scrap, which is still available to be recycled after end of life, and creating that into a pure form of steel. That is a very low emitting process, with scope 2 emissions being just 0.3 tons per ton of steel, and scope 1 emissions being 0.04 tons of CO2 per ton of steel. The more prolific version of steelmaking actually is the version which we just described, which uses the iron ore and converts that into a more pure form of iron that's then available for steelmaking. That is more intensive in terms of emissions, with scope 1 and 2 emissions ranging between 1.4 and 2.2 tons of CO2 per ton of steel. If we were to look at the relative proportions of steel being made using each of those methods, the first one is around 30% and the second one is around 70% of production. So again, why steel is considered a hard to abate industry is because there are currently no commercially viable zero carbon alternatives for coal as the reductant in bulk steelmaking. But that doesn't mean the industry is doing nothing. There are several opportunities in the long and short term to remove carbon. They include operational efficiency improvements, which are basically the low-hanging fruit, finding an alternative reductant to that coal, and that is the holy grail, sourcing energy from low carbon sources, carbon capture and storage or usage, improving subsequent steel processing, offsetting in the interim period, and bringing steel more into the circular economy to reduce primary steel demand. A common question that I get asked, and is probably the elephant in the room, is why do we not just use recycled steel and use that electric arc furnace process, that the first low emitting process? And the reason for that is that there isn't enough scrap available in the global market to meet global demand for steel. However, as you see moving forward, the component of scrap that contributes to that yearly output is going to increase. However, the demand for primary iron ore based steelmaking is still going to exist. And that's why it's really important for us to start decarbonising that process in particular. There are many demands for steel mills to convert to a process that is low and zero emitting. That will be mainly coming from shareholder demands as well as regulatory impacts. But there is also a financial imperative. So that pressure is also coming from the financial impact, with a McKinsey report showing that through a study of 20 global steelmakers, the weighted average value at risk was around 14% of net present value, and that ranged up to 30% for individual companies. Of course, at that global level, we want to set science-based targets, and the Science-Based Target Initiative has set high-level targets across the sector. However, that's not going to be able to deliver the net carbon reductions that we require, and that's because the sector is treated homogenously. So it wouldn't make sense, because of those two methods of production being used, to assign individual targets to individual steelmaking mills on the basis of the volumes that they produce. It has to take into consideration the methods that they are producing that steel by. In addition, the Scope 3 emissions under the Science-Based Target Initiative has some issues around how it's being reported and dealt with. And so the Science-Based Targets Initiative is planning a collaborative project with the steel industry to develop a specific steel sector guidance. In the meantime, the industry itself has released a report earlier this year in July. In that report, there is a definition around how we could actually determine allocations for individual steel mills based on the production process and volumes. It accounts for the decarbonisation of primary and secondary sources, defines the scope of what emissions should be included in a science-based target, accounts for the contribution of co-products produced within the boundary of the steel sector that are utilised outside of the steel sector. An example of that would be aggregates that are used in roading but don't have any metallic content at all. And defines a pragmatic accounting mechanism for consistent implementation. At that global level, we also have to look at the raw materials, and the Responsible Steel certification program has just undergone a consultation process to look at that very issue. And I am aware that Bluescope Steel has put their hands up to be a pilot for that certification program. And Bluescope Steel is the parent company of New Zealand Steel. That holy grail of replacing coal as the reductant has led to a lot of research around hydrogen as the alternative. That would mean that instead of CO2 being the byproduct, it would be H2O, so water would be the byproduct, taking that off. So basically the hydrogen is taking that oxygen away instead of a carbon atom. However, it's not trivial research, as it requires examining the kinetic limitations and thermodynamic processes. So it's a complex research program. You have to look at how to produce zero carbon hydrogen, then look at the steel making process, and then how the iron making process that would utilize the alternate reductant, and then look at the steel making process that uses the alternate iron process. The program that has the most potential, it looks like, and is certainly the most advanced, is the hybrid project that's happening in Sweden. It's an awesome collaboration across the channel. So it includes SSAB as the Sweden's primary steelmaker, LKAB on the iron making side, and Vattenfall on the energy side. And this project is aiming to use hydrogen as the alternative reductant to coal, and would lead to an anticipated reduction in Sweden's total CO2 emissions of 10%. There are 6 sub-projects under this program of work. Most of those, 5 out of the 6, are on the technical side, so looking at the hydrogen production, the iron production, and then the steel making. And then there is a 6th program, which I think is quite interesting, which is basically looking at the channel development required to take this to market, including looking at the policy settings, which is a really important part of decarbonisation of any industry. The project is running ahead of schedule, and earlier this year they created their first zero carbon steel using this process, and that was destined to a niche application in automotive manufacturing and used by Volvo. So there's certainly not at the level that it could be used for those applications in infrastructure that we ran through at the beginning of this presentation. And it's anticipated, for example, that SSAB won't be at net zero carbon across all of its operations until around 2045. And a big part of that is that with steel making, there's a lot of invested capital worth large amounts of money that have long lifetimes. And so it's really important to be able to take into consideration new and emerging technologies when those large pieces of capital are being reviewed for upgrading or replacement. So there's a lot happening internationally, but of course we need our local steel supply chain to be low carbon. And what's happening in this area? So earlier this year, in February, Bluescope appointed Greta Stephens as the Chief Executive of Climate Change. That was the first time they had a role on the executive team with that responsibility. And the reason why that's of interest to New Zealand is that Greta is also the Chief Executive of New Zealand Steel. Bluescope also released its first climate action report in September this year, and in it they announced their process to get to their target of 2050 net zero greenhouse gas emissions, as well as a 150 million 5-year climate investment program. And there's a lot of detail in that report, and I would definitely recommend people read that, but I'm going to show you two parts of that report that I think are important. So here we can see how Bluescope is planning to deliver its net carbon, zero carbon 2050 target. So basically it has an initial focus on that low hanging fruit. So the energy process efficiencies, the low carbon energy sources, increased scrap use, then starting to invest and work with emerging technologies towards around 2030, starting to bring in some of those breakthrough technologies around hydrogen direct reduction of iron making. And they anticipate there may be still a requirement for some offsetting to meet that target in the longer term. In terms of that $150 million investment program, again, it's focusing on the low-hanging fruit initially with raw material resource efficiencies, waste heat and gas recovery, increased procurement of reliable renewable energy, as well as the investment in those emerging technologies. So that might include a pilot electrolyzer to accommodate the hydrogen injection in the blast furnace process, looking at biochar, scrap melting technologies, starting to invest in some of the emerging technologies and looking at optionality when those capital investments are coming up for consideration. And then investigating and participating in those breakthrough technologies being developed, including direct equity investments and piloting of those. And I think it's useful to note that Rio Tinto and Bluescope Steel just recently signed an MOU. That was last week. So what are we in? We're in mid-November. So just a couple of weeks ago. And that is a commitment for them to work collaboratively to develop zero carbon iron ore processing, or low carbon iron processing, and taking some of, I would think, the Pilbara iron ore and making sure that it's suitable for any future processes which would enable zero carbon steelmaking. It's also interesting to note that a few weeks ago also there was an announcement that there will be a large hydrogen fueled energy plant created at Port Kembla. And Port Kembla is geographically very close to where Bluescope Steel's primary production happens in Australia. And although there have not been any announcements either from Bluescope or from that MOU in relation to that MOU being signed between Bluescope and Rio Tinto, I think it makes natural sense that that location for that hydrogen plant is so geographically close to the steelmaking process. So I would think that there would be announcements forthcoming around that. Although I do not have any insider information, and Bluescope have not made any public comments about that. So in terms of that low-hanging fruit, what are the operational efficiency improvements that can be delivered? For example, one of the, I guess, unknown, little known things around New Zealand Steel's production at Glenbrook is that 92% of its electricity comes from renewable resources and on-site cogeneration from off gases and waste heat. So New Zealand Steel recently collaborated with its supplier of cogenerated electricity, which is Linter Energy, to improve that production. This 3-year project resulted in a near 10% increase in on-site electricity generation, worth around 55,000 megawatt hours per year. And that represented around 5% of total electricity requirements at New Zealand Steel's Glenbrook site. And that reduced requirements for grid electricity generation by around 6,500 tonnes of CO2 equivalent per annum. So there are some quite substantial gains that can be had just from delivering on those low-hanging fruit. Similarly, Fletcher Steel, which is basically a receiver of some of New Zealand Steel's steel, as well as an importer of steel, to coat, for example, for the colour coat product. They just received GIDI funding to decarbonise that steel coil coating process. And at the completion of that work, Fletcher Steel's fossil fuel consumption will be reduced by up to 89%. And have a resulting reduction in CO2 equivalent emissions of 67%. And that's against a target of 30% reduction by 2030 that was originally set for Fletcher buildings. And I think it's important to note here that I understand that this was the first time that a capital project was approved on the basis of decarbonisation within the Fletcher Group. So that was the reason that capital program went ahead. And it also is showing the importance of government investment to support the private sector to be able to go that last little bit towards decarbonisation in terms of getting the capital investment projects over the line. Of course, we must also find an alternative reductant for our steelmaking. And why is that important? Why don't we just piggyback off the work that's happening in hybrid in Sweden? The reason for that is that New Zealand Steel's steelmaking and iron making process is unique in that it doesn't use iron oxides coming from iron ore. It uses iron sands that are locally mined in New Zealand. So we couldn't just take that hydrogen reduction technology from the hybrid project and plug it into the iron making process at New Zealand Steel. But there is work happening through the Robinson Research Institute at Victoria University of Wellington through Chris Bumby, looking at a specific reduction process there associated with iron sands steelmaking. And I do know that Bluescope Steel have invested in that research, and HERA and probably the Sustainable Steel Council are planning to do so as well. Of course, we can't wait for that to happen. We need to be zero carbon now. So what are we doing? HERA has just, we are just about to launch a comprehensive and world first zero carbon steel offsetting program that will enable the offering of zero carbon steel product in New Zealand ahead of us being able to deliver that holy grail of the alternate reductant. The calculator has been developed, that sits behind that program has been developed independently by ThinkStep, and it uses robust data, for example, coming from environmental product declarations and LCA data. The offsetting will happen through ECOS. We have got a particular focus on Indigenous and native forest planting and regeneration so that we get that additional biodiversity benefit as well. The program itself covers off pretty much the broad range of steel products in New Zealand. So everything from roofing and cladding to light gauge steel framing to heavy steel that you might see in a bridge through to reinforcing rebar and including stainless steel as well. We also need to move away from just focusing on steel production and look at the whole channel going on a low carbon journey. So what are we doing in that regard? New Zealand has a Sustainable Steel Council. I'm the chair of that council currently, and it has a certification scheme against Treasury's Living Standards Framework. We estimate that around 70% of structural steel supply now is coming from certified fabricators. And we also have a Aotearoa Steel Transformation Agenda and Plan that also uses the Living Standards Framework, and in it there are commitments to moving to zero carbon operations. And the plan and the agenda covers the whole supply chain, right from manufacturer to fabricator, roll former, and also including the industry associations and research associations. So for example, HERA has signed up against the Charter and Agenda, and in that we've committed to becoming net zero carbon operations, and we are in our 3rd year of being certified net carbon zero. Of course, if our objective is to reduce net carbon emissions, we have to stop talking about embodied carbon and start talking about lifetime carbon emissions. And we need to start talking about circularity in our economy, because that is what is going to have impact. If we look at carbon just at the point in time that a building is constructed, we lose all of the data and information around what happens to carbon at the end of the life of that building and during the operations of that building. Steel is actually a leader in New Zealand's circular economy. 72% of steel in New Zealand is recycled. We know this because we commissioned a report from ThinkStep that shows this. The collection of 545 kilotons of steel scrap every year from New Zealand provides a net benefit of 793 kilotons of CO2 equivalent. That's worth around 1,050 kgs of CO2 equivalent per tonne of steel scrap. That would increase to 1,106 kilotons of CO2 equivalent per year if 100% of steel scrap was collected for recovery, obviously because it would no longer be going to landfill. And that would be contributing around 1,500 kilograms of CO2 emissions reduction per tonne of steel. Steel is one of the most recycled materials on Earth. If not the most recycled material. For example, the steel that would have been in the original Holdens would probably be in circulation somewhere in another application globally. Of course, in terms of circularity, it's not just about recycling, it also includes reuse and repurposing, and extending the lifetime of those products. So HERA is also in the process of developing Australasia's first material passport to facilitate improved reuse and repurposing of steel products. The way to look at material passport would be, it basically gives the information and collects the information and stores it that would enable a building or a piece of infrastructure to basically be considered a bank of materials that's then available for reuse at end of life. Material passports are unknown in New Zealand, but they're becoming more, well, basically there's research happening mainly in EU, and it looks to have some fairly good promise in terms of being able to facilitate that circularity. Another key project that we're working on is to extend the lifetime of steel products. So for example, where the building code requires 50-year lifetimes, how do we change our specification upfront to enable the lifetime to double to 100 years? That creates a longer life where carbon can be amortized over a longer period of time, but also reduces that requirement for primary steel production. So as the sector does transition to 100% circularity, either through recycling or reuse or repurposing, and we move towards zero carbon emissions, either through offsetting or through having zero carbon primary production, the sustainability credentials of steel would be very hard to challenge.